All right, here's the rest of the lecture for today's lesson over proof structure. I'm going to go over this example again, but you may have already seen this in class. So for this first example, these are the type of proofs that you will need to do on the homework assignment. We are given that 5x minus 18 is equal to 3x plus 2, and we're asked to prove this. So again, to do a proof, we have two columns here. In the left column, we will write our statements. And in the right column, we will write the reasons that justify those statements. So the first statement you always start out with is the given. So 5x minus 18 is equal to 3x plus 2. The reason that we know that that is true is because it was given to us. All right, so what I would like to do is basically to prove that x is equal to 10 is true for this equation. In order to do that, I'm going to use my algebra steps just like you would in Algebra 1. The first thing I would do is get all my x's on one side by using the subtraction property of equality. And in the future, we would just write subtract and abbreviate this. But I'm going to use the subtraction property of equality, which says that if I subtract 3x, as long as I do it from both sides, the equation is still true. So if I subtract 3x, 5 minus 3x is 2x, minus 18 is equal to 2. So again, since I subtracted it from the 5x and the 3x, eliminating it, as long as I did it to both sides, then any values of x that were true that satisfy this equation should be the same values of x that satisfy this equation. All right, I have two more steps to solve this for x. The next step is I would want to get rid of this minus 18, and I would do that by adding the addition property of equality, and I'm adding 18 to both sides. So if I do that on the left, I'll have 2x. On the right, 18 plus 2 is 20. And then the last step to get x by itself here would be to get rid of that 2, which I would do by the division property of equality. Or basically, I'm going to divide 2 from both sides. On the left side, that leaves me with 1x. On the right side, that leaves me with 10. And again, that's what we're trying to prove. So you should notice a few things about the proofs as you do them more and more. The first statement is always your given. The reason why it's true is because it's given. And then the last statement is always what you're trying to prove. You just need to fill out these boxes in the middle with the statements and then reasons that can get you from this initial given to what you're trying to prove. All right, so I'm going to have you try this. So what I would like you to do is pause the video and see if you can go through this process for yourself. And then when you're ready, hit resume, and I will show you what my answer is. All right, hopefully you got this as your answer. The first line you should have wrote was to copy and paste our given statement down here, 55y minus 3 times the quantity 9y plus 12 is equal to negative 64. And that's true because it's given to us. And then the first thing you would do to solve this would be to distribute the negative 3. If you do that, you'll get 55y minus 27y. Remember, you also have to distribute it to the 12 to get negative 36 equals negative 64. Again, the reason why this is true is the distributive property. The next thing I would do is combine like terms. So 55y minus 27y is 28y minus 36 is equal to negative 64. And again, that was simplifying by combining like terms. Then I would add 36 to both sides to get 28y is equal to negative 28. And then last is I would divide by 28 to get y equals negative 1. So again, really, all that changes is instead of showing your work in the problem, you write your work out to the side on how you get each next step. All right, the next thing that we're going to do is we're going to go over two other examples that have us prove not algebraic, but instead we're going to prove geometric theorems that we have had in class. I'll move this somewhere. Let's move it down here for now. Oh, actually, we can move it over here. This is perfect. All right, so what I want to do is prove the vertical angles theorem. So the first thing you have to know is, what is the vertical angles theorem? The vertical angles theorem states that vertical angles are congruent. All right, so how would I do that? Well, let's identify a pair of vertical angles in here. So we have, let's try to prove that angle W here is congruent to angle Y. So again, on the left side of this proof, I'm going to have my statements. And on the right side, I'm going to have my reasons. Now, it might look like we're not given anything in this problem, but actually we are. We are given this diagram to use. So what I would start with is I'm given a diagram. And that is given. The reason I know that that diagram is true is because that was given as a part of the proof. All right. The second thing I will notice is, all right, I can't use the vertical angles theorem to prove the vertical angles theorem is true. So I have to find another way to relate W and Y, and hopes that that can give me some way to show that they are in fact the same measure as each other. To do that, I might note that angle W and X here have a relationship, and that X and Y shares that same relationship with them. So I think I can use angle X here to show something is true for both W and Y, and as a result, W and Y must be congruent. All right, so let's talk about how we would do that. Note that W and X here make a straight angle. So we can say that the measure of angle W plus the measure of angle X is equal to 180 degrees. And that is the definition of, now your choices here are, there are many ways you can say, I know this is true. The definition I'm going to use is the definition of a linear pair. Since W and X together make a linear pair, then they must add up to 180. So again, you could have said the definition of supplementary angles, or you could have said the definition of a straight angle. I think all of those would be true reasons as to why we know these two angles have to add up to 180. Similarly, Y and X also make a straight angle. So I can say that the measure of angle Y, let's try that again. Measure of angle Y plus the measure of angle X is equal to 180 degrees. And again, I'm just going to use quotation marks because that's true for the exact same reason. X and Y are also a linear pair. All right. Now we're going to use a little bit of algebra. Note that both of our equations here are equal to 180, which means that if both of these are equal to 180 degrees, then that must mean that they are also equal to each other. And that's the substitution property of equality. So I could say the measure of angle W plus the measure of angle X is equal to the measure of angle Y plus the measure of angle X. Since they are both equal to 180, that means they must be equal to each other. And again, that's substitution. Or you could have said that this is the transitive property. Either answer would be fine there. All right. Now you'll notice that since I have an X on both sides of this equation, if I was to subtract that out, it would eliminate it on the left side and on the right side, leaving me with the measure of angle W is equal to the measure of angle Y. And again, that's subtraction property of equality, and what I subtracted was the measure of angle x, and I did that from the left and the right. Hey, and here we go. We now have what we were trying to prove, that they are at least very close to what we're trying to prove, is that the measure of these two angles have to be equal to each other. And that means that angle W is congruent to angle Y. That's the definition of congruent. So there we go. With this diagram, we were able to show that these vertical angles, W and Y, are congruent because both of them are linear pairs with X, which means that they have to add up to 180 with X, which means both of these equations equal each other by the substitution property of equality. And if I subtract the measure of angle X away from those equations, I'm left with the measure of angle W has to be the same as the measure of angle Y, which means, by the definition of congruent, that they are congruent. Yay! All right, eventually, we're going to want you to be able to do all of this by yourself. But right now, the goal is that after this lecture, you should hopefully be able to, using this, having this available to you in your notes, explain this train of reasoning to a friend or to another student that missed class. If you leave this lecture being able to walk through and explain why each of these statements are true and why this proof means that vertical angles are congruent, then you're in a good spot. If you're not, that's okay. You can rewatch this video, ask me questions in class tomorrow, or there's always other videos that you can look up online and see if they can help you out as well. All right, let's do one more, and then that'll be it. All right, let's prove one more geometric theorem. We want to prove the corresponding angles theorem. So again, the first thing that you might have to ask yourself is, what is the corresponding angles theorem? The corresponding angles theorem is actually technically two-directional. We're only going to prove one direction of it, that if line, in this case, it'll be AB, is parallel to line CD, then their corresponding angles are congruent. So it's similar. We're doing a congruency proof, just like we did it before. Only this one, we're given this, and we're trying that the two lines are parallel. And hopefully from that, we should be able to prove that the corresponding angles, which again, in this case will be angle 1 and angle 2, are congruent. So on the left, we're going to write our statements. On the right, we'll put the reasons. First line is, I'm going to say that I'm given, in fact, I'm actually given two things in this proof. I am given that, I'm given the diagram, but I'm also given this conditional statement. It says, if this is true, then that. So we are going to assume that this is true and see if we can show logically that that means the corresponding angles are congruent. So the diagram is going to be true, and we're also going to say that AB is parallel to CD. Okay, those are the two things that we are given. All right, step 2. All right, so if all we're given is this diagram and the fact that these two lines are parallel, what does that mean? What that means is, if these two lines are parallel, then that means this transversal here is going to have to intersect them at the same angle. All right? So what we can say is line GE or GH intersects AB and CD at the same angle. At the same angle. I ran out of room here. That's okay. Okay, same angle. And the reason why that's true is the parallel postulate. It gets actually, the details of that get a little bit more confusing, but the parallel postulate is an assumption that we make in mathematics in Euclidean geometry, where for every line parallel to another line, there's only one line, GH in our case, that could intersect those two at two given points. So if I put a point on AB like E and a point on CD like F, and I draw a line through them, there's only one line that can intersect or go through those 2 points, which means that we get a definite angle. It's not like there's another line GH that I could draw that could pass through both F and E. Right, that's the parallel postulate. So if we assume that that's true, which we will since we're doing Euclidean geometry, then we could say that these intersect at the same angle. If that means that these intersect at the same angle, then that means that the measure of angle 1 is equal to the measure of angle 2. And again, that follows from our second statement. Oh, actually, hold on. Actually, I'm getting ahead of myself. Hold on. Before I write that, no, that's okay. I can write that here. I can do that. I was going to do this in a different order, but that's okay. And then we're going to use that same idea. Since these are intersected at the same angle, which means that these two angles are the same, then I can say that angle 1 is congruent to angle 2 by the definition of congruent. Remember, congruent means that two objects are the same shape and size. If these angles have the same size, then they're necessarily the same shape. So these angles are congruent. They have the same measure. All right, and then the last line is I do need to note, it was kind of implied in the previous one. Some people would technically want some definition in there for the previous example about vertical angles, that they were vertical angles. I don't think that was super necessary because I think the vertical angle theorem doesn't really rely on that, at least when we were given that diagram. But for this one, you absolutely would want to say that what this means, since angle 1 is congruent to angle 2, then that means that corresponding angles are congruent. And again, the reason why that would be true is because by definition of corresponding angles, angle 1 and angle 2 are corresponding. Okay, so that is a proof of the corresponding angles theorem, that given two lines are parallel, that means that since the lines are parallel, a transversal GH is going to intersect them at the same angle according to the parallel postulate. It follows from that then that angle 1 and angle 2 have the same measure. If they have the same measure, that means that they are congruent by the definition of congruent. That's what it means. If angles have the same measure, then they are congruent. And finally, since the definition of corresponding angle tells us that angle 1 and angle 2 are corresponding, right? They're in the same position. They're both in the bottom right of this intersection. Then we can conclude that all corresponding angles are congruent. Now, if you transfer it in or transfer it out to another class, this may not be the exact proof that another teacher would use, we could get a little bit tighter in our definitions, maybe make this statement here that we kind of bundled in here, its own statement. Angle 1 and angle 2 are corresponding angles by the definition of corresponding, and therefore then they are congruent. Therefore then all corresponding angles are congruent. Or more commonly, a lot of other teachers will not teach you about the parallel postulate, and they will just say, we are going to assume that all corresponding angles are congruent as a postulate instead of proving it. So again, the goal here is for you not to be able to recreate all of this on your own. That is not the expectation for my class. Instead, what I would like is, as long as you copied down in this note, this into your notes, you would be able to use this to complete other homework assignments, other homework questions, to fill in blanks and other proofs, but also to be able to explain how this proof works, being able to say what each statement means and why each statement is true to a friend or another student that may have missed class. All right, that's the end of today's lecture. What I would like you to do then is begin working on homework 2.4, which will be due Wednesday. If you have any questions, please let me know. Thank you.